Welcome back, everyone, to the final session of EnviroTech, our virtual version. Probably one of the most important topics out there right now with emerging contaminants. So I'll turn it over to Zara Friani with Stantec. And when we're done the 5 presentations, I'll come back with some closing comments and wrap things up. So I'm going to turn it over, Zara, and you can take over and start with the first presentation.
All right, thanks so much, Joe. Happy to be here, happy to be involved. I'm not going to spend too much time on introducing each speaker just because we don't have too much time for each, but what I'm going to do is ask each presenter to give a like 1-2 sentence introduction of yourselves and your presentation prior to starting. Each presentation is 25 minutes and we have 5 minutes for questions. So our first presenter there is Matthew Cody at SLR Consulting. I'm just going to switch Matthew here.
Great. Oh, let's see. Got to get my cursor on there. Excellent. How is that looking?
Oh, perfect. Great.
Okay.
Great. Okay. Go ahead, Matthew.
Alrighty. Okay, great. Thanks, Zara. So I've been with SLR Consulting for 10 years now, working in the risk assessment group. For the last 6 years, I've been supporting Lindsay Patterson, a few others with the assessment of PFAS impacted sites across British Columbia. And so that kind of is a nice segue into my presentation today here, titled a review of environmental management considerations for firefighting foams containing per and polyfluoroalkyl substances. Some of the material that was touched upon in an April ESAA webinar given by Lindsay Patterson and myself will also be kind of covered in this presentation as well, and so there'll be some segues. Let's see here if that's going to work for me. Great. So as part of that talk, we went through some of the main sources of PFAS to the environment in Canada. Some of these sources include landfills, wastewater treatment facilities, biosolid application areas, and food waste compost. But generally, the most well-known source of PFAS to the Canadian environment is the use of Class B firefighting foams. Class B foams are used specifically for extinguishing flammable liquid fires, whereas non-flammable liquid fires, termed Class A fires, are more commonly extinguished with Class A foams that are not known to contain PFAS. Class B foams are used by a variety of industry and service groups, including but not limited to municipal services, specifically local fire stations, flammable liquid processing and storage facilities, including the various streams of the energy sector that handle large volumes of flammable liquids, and military operations and airports. Of those groups, military installations and airports have been receiving the most attention in the last few years. This is a figure from 2018 Royal Military College of Canada publication, where the authors attempted to estimate the number of airports in Canada that were potentially or likely contaminated with PFAS from Class B foams. They estimated that approximately 175 airports in Western Canada, so that's BC, Alberta, Saskatchewan, and Manitoba, were considered to be likely or potentially contaminated with PFAS. The figure on the left, so the bottom left, which might be difficult to see in detail, shows those sites that are potentially contaminated with PFAS, represented by the dark gray dots, or likely contaminated with PFAS, represented by the light gray dots. So clearly the number of sites impacted by Class B foams is quite extensive. And that's one of the takeaways from our April webinar, is that you really don't need to release that much fluorinated foam to create a contaminated site. As I previously mentioned, Class A foams are not expected to contain PFAS. Foams containing PFAS are Class B foams, but it's important to be aware that not all Class B foams contain PFAS. Very confusing. There are numerous non-fluorinated Class B foams on the market now, which are presented on the right side of this table, that have been receiving a great deal of attention and are being adopted by government and industry as viable alternatives in certain instances, considering some of the human health and environmental concerns associated with PFAS. But the fluorinated foams are still the dominant products on the market and dominant products used by the aforementioned industries and services. I won't go too deeply into the specifics, but there's really been an evolution of Class B foams over the years. The methods used to create the PFAS in the foams have evolved, and the formulations themselves have evolved to meet industry and condition-specific requirements for extinguishing flammable liquid fires. Modern foams have also transitioned away from using long-chain PFAS like PFOS as these long-chain chemicals are generally understood to be more readily accumulate in food chains and generally understood to be more toxic. The chemicals that are present in Class B foams vary by product, but based on the information presented in the literature and available on material safety data sheets, the primary ingredients include water and glycols, which are the solvents that make up the largest fraction of the solution. Then there are the modifiers, which include chemicals that adjust pH, improve operation in extreme temperatures, and enhance shelf life, for example. Then there are the non-fluorinated surfactants that enhance foam generation. And typically there are the fluorosurfactants, or the PFAS, with their unique chemical structure and behavior that I'll discuss on the next slide. When these ingredients are mixed with water, the resulting solution achieves interfacial tension characteristics needed to produce an aqueous film that spreads across the surface of a liquid fuel source to extinguish the flame by forming a vapor barrier between the liquid fuel and the atmosphere. And that is why these products are also called aqueous film forming foam, or AFFF, which is a term used elsewhere in this presentation. So when considering the environmental implications of foams, it's clearly important to be cognizant of the full ingredient list. For example, these products contain glycols that have the potential to contribute to the depletion of oxygen in aquatic receiving environments. And some formulations have biocides that may also present risks to living organisms. However, it's the PFAS ingredients that are generally understood to pose the greatest concern due to their behavior in the environment. So what are PFAS? The term PFAS encompasses both per and polyfluoroalkyl substances, a family of thousands of chemicals. The most recent estimate from the United States Environmental Protection Agency is that up to 4,700 individual PFAS chemicals may have been or may currently be on the global market. The perfluoroalkyl substances are those chemicals that are comprised of a carbon chain where the carbon atoms are completely surrounded by fluorine atoms or are fully fluorinated, represented by the green circles on these molecular representations. Polyfluoroalkyl substances refer to those chemicals where the carbon chain is only partially fluorinated, so only a portion of the molecule is green or fully fluorinated. In the lower representation, the blue circles represent carbon atoms that have hydrogen atoms attached instead of fluorine. PFAS can have any one of a number of functional groups at its head, so being the red circles on these representations. Functional groups like carboxylic acids or sulfonates. We tend to distinguish PFAS and name them based on the length of the carbon chain in the compound. Short chain PFAS have fewer than about 6 green parts, and long chain PFAS have more than that. The main point to remember about the structure is that the green or fully fluorinated portion of the chemical is extremely persistent in the environment, regardless of carbon chain length due to the strength of the carbon-fluorine bonds. Class B foams contain a multitude of PFAS species, including anionic, cationic, and zwitterionic surfactants. A 2017 publication by Dr. Jennifer Field out of the University of Oregon identified 57 classes of PFAS in Class B foams acquired from US Air Force bases. A significant portion of the PFAS in Class B foams are polyfluoroalkyl chemicals that are termed precursors because these chemicals will ultimately degrade down to terminal perfluoroalkyl acids that are incapable of further degradation in natural situations. These precursors are the unknowns of the PFAS world. They are proprietary chemicals in these formulations that vary by manufacturer and product, and not a whole lot is known about them. This is a figure taken from that Dr. Field study that I alluded to, where it shows the transformation of one precursor called 6,2-fluorotellumer thiamidosulfonate. You can see it break down to a few intermediaries, then into 6,2-FTS or 6,2-fluorotellumer sulfonate, and finally transform into terminal products like perfluorohexanoic acid, perfluoropentanoic acid, and perfluorobutanoic acid. There is evidence to suggest that the precursor chemicals in the modern formulations readily transform to the 6,2-FTS, but transformation of 6,2-FTS to the perfluoroalkyl acids occurs much more slowly. So significant concentrations of FTS can be present at foam sites after many, many years of dispersal. And that's really the big takeaway, that with many of these products, you're starting with often with a mixed bag of PFAS, and you're not necessarily going to detect these PFAS by limiting your search to perhaps those commonly assessed for chemicals, like PFOS or PFOA. With modern Class B formulations, while they reference that they are C6 formulations and don't contain PFOS or PFOA, they still contain PFAS, including precursors that are either currently regulated in Canada, precursors or terminal products that are either currently regulated in Canada or may be regulated in the future. So what are the concerns? As just mentioned, PFAS are extremely persistent. Some PFAS are known to bioaccumulate in the tissues of humans and ecological receptors. And there are known human health impacts and there are known health impacts to humans and ecological receptors exposed to PFAS. And once released to the environment, PFAS are capable of being highly mobile. So to convey the mobility and persistence points, this is a schematic of a PFAS groundwater plume from an unnamed site where SLR has been supporting environmental management activities. There are a number of factors at play here affecting PFAS migration in groundwater, including some salinity effects from the nearby marine environment. But one of the key takeaways is that those short-chain PFAS like perfluorohexanoic acid, perfluoropentanoic acid, and perfluorobutanoic acid, so represented by the orangey colors in these relative proportion charts, have less of an affinity to sorbing to soils, and as a result are quite mobile. And as you can see in these charts, the proportion of these short chain PFAS increases relative to the fraction of the long chain PFAS, so like PFOS or PFOA, the further you move away from the source area. So on this slide, the source area is kind of that purple ring at the top there. There are examples of PFAS plumes that are many kilometers in length with little fluctuation in concentration over the length of the plume. And so from a human and ecological health perspective, while the transition away from the long chain PFAS is clearly a step in the right direction, the short chain PFAS are just as persistent, are even more mobile, and still appear to have a toxic effect to humans and ecological receptors. And it's these short chain PFAS that are still being used in some Class B foams. So in terms of regulatory considerations that those using Class B foam should be aware of, at the international level, there's the Stockholm Convention, a UN international treaty which aims to eliminate or restrict the production of persistent organic pollutants. Both PFOS and PFOA have been added to Annex B of that treaty. And then there is the Basel Convention, which is another international treaty that aims to reduce the movement of hazardous waste between nations. There are now limits set for the levels of PFOS and waste that can be moved across borders. In Canada, at the federal level, PFOS and PFOA and long-chain perfluorocarboxylic acids and their salts have been identified as toxic substances under the Canadian Environmental Protection Act. Currently, there are exemptions that allow low levels of these PFAS in Class B formulations. However, there are now proposed amendments to remove these exemptions. So I won't go into detail into the environmental quality guidelines that are applicable once PFAS enter the environment. Rather, I'll encourage you to attend the webinar that will be presented by Lindsay Patterson and Ian Mitchell later on in this session. But one point I'd like to make is that the study of PFAS in the environment is still in the relatively early stages. And as we begin to learn more about the human health and environmental implications of PFAS, we're going to see the regulations guiding the use of these chemicals and their management in the environment evolve. We're going to see more PFAS becoming regulated, and there will likely be a trend with standards and guidelines becoming more stringent with time. So in light of what we know of the fate of PFAS in the environment and the associated environmental liabilities, that really puts the onus on those using these products containing PFAS to ensure they're doing everything in their capabilities to limit the release of these chemicals to the environment. And when a release does occur, to do everything in their power to limit the scale of contamination and mitigate potential impacts. And for those using Class B foams that contain PFAS, the most effective tool to help minimize risks is to develop a foam environmental management plan for each respective operation or facility. I'm talking about a living document that is updated by employees and that employees are expected to be familiar with. The foam environmental management plan should really cover the full life cycle of a foam, as presented in this diagram made available by the National Academy of Sciences, Engineering, and Medicine. The ultimate objective of the plan is to ensure that you're doing everything in your power to reduce the probability of release while at the same time developing contingency plans for all the possible release scenarios. But even before that, the plan should outline some procurement considerations for those that are purchasing products for a facility or operation. So obviously, when evaluating Class B products, the primary goal is to protect human lives and limit damages to infrastructure. And therefore, product selection should ultimately be directed by which product has the best efficacy results, meaning how quickly a product extinguishes a fire and controls burn back, while at the same time verifying the product is suited for site-specific conditions like the fuel source at hand, environmental conditions, and technical requirements of dispersal equipment. And also, a given sector or industry may have specific standards that must be achieved. For example, the aviation industry in Canada has performance requirements as part of the Canadian aviation regulations that dictate what type of products can be used and the standards that must be achieved. One interesting side note is that an exemption has recently been made by the Canadian airport regulations, that allows airport operators to adhere to the International Civil Aviation Organization standards, which ultimately allows Canadian airports to use fluorine-free foams. So on that note, an interesting little side story is that I've been in communication with Mark Smith, who is the fire chief of the Billy Bishop Airport in Toronto, which is the first and so far the only airport in North America to have made the transition to fluorine-free products. Mark and representatives from Perimeter Solutions, which supported the transition to the fluorine-free products, confirmed that the modifications to the fire trucks and emergency response equipment to allow them to use the more viscous fluorine-free product were not overly extensive. Another item that Mark mentioned was that a number of larger Canadian airports have reached out to him seeking guidance to support their transition. So there is definitely an interest out there, and I would expect we'll soon be hearing about other airports that have made the switch to the fluorine-free products. So back to the procurement considerations. So once the efficacy data has been considered, the next step is to determine which of the products under review are more environmentally benign. And at this step, you should start with the ingredients list. While some information can be obtained from the product information sheets or the material safety data sheets, in the best case scenario, the manufacturer will be willing to provide the ingredients list through a non-disclosure agreement. So ideally, you'll be able to obtain the chemical abstract numbers for all the chemicals in the formulations, including the PFAS. And from there, you can look into the literature for toxicity information pertaining to the chemicals and the PFAS, or at a minimum, this will allow you to verify that the chemicals or the PFAS used in these formulations are indeed C6 chemicals proclaimed in the information sheets. And this will also give you some insight into the terminal PFAS that you would expect to see following transformation. Toxicity information for the products may also be helpful, but it's important to recognize the shortcomings of this data. Toxicity data on MSDS sheets generally consists of the ATE mix values that are calculated values derived from generic toxicity values for those chemicals that fall into acute toxicity hazard categories and that form more than 1% of the composition of the mixture, and as per the hazardous product regulations. And just a note, I've not seen any specific PFAS listed in the ingredients list of an MSDS sheet. Rather, you'll see terms like fluorosurfactant or polyfluorinated alkyl betaine or fluorinated amphoteric surfactant. But when you see fluorinated or fluoro, you know you're dealing with PFAS. And if you don't see reference to fluorine, that doesn't mean it's not in the product. And in these scenarios you should follow up with the distributor or manufacturer to confirm. So if your operation or industry allows for the use of fluorine-free products and the product can achieve your standards or objectives and you can make them work with your equipment, then consideration should definitely be given to procuring fluorine-free foams. If not, and it's determined that fluorinated Class B foams are still needed, then it is of value to determine if you can use a multi-foam approach, which could include using fluorinated Class B foams in some scenarios and non-fluorinated foams in other situations. And a note of caution, if you've received donated products or have older products in your inventories, you'll really want to do your due diligence to verify that you have a modern C6 formulation, as older foams can contain PFOS that are prohibited under SEPA or may contain other long-chain PFAS that have a particular concern for uptake into the food chain. When considering storage and handling, you'll need to ensure that all foams are clearly labeled. Fluorinated foams have been isolated from non-fluorinated foams, and all foam products are stored in secured areas. Regular inspection of pre-charged systems should be completed to ensure systems are functioning and aren't leaking. If using a multi-foam approach when changing between products, it's important to thoroughly decontaminate equipment when transitioning from a fluorinated product to a fluorine-free product. When planning for the disposal of older or expired products and the waste gathered from decontamination events, it's important to do your research when selecting a facility that, and to verify that you're selecting a facility that is actually capable of receiving and treating your waste. On the training and testing side of things, fluorinated foams should not be used for training. Rather, water or fluorine-free foams specifically designed for training should be used. There are also specialized fire training facilities out there that are designed to contain and collect all runoff. And there are technologies on the market that allow you to test your equipment without any product actually being released to the environment. One example includes the Ecologic mobile testing system developed by E1, which is presented on this slide here, that allows for direct connection to the nozzles of fire trucks. This technology is currently being used by the Canadian Department of National Defence, as are other technologies directly developed by DND, like containment bags that can be connected to the end of fire nozzles so that all the foam released is immediately contained. As part of planning for a release event, the foam environmental management plan should identify a list of procedures that should be followed for each conceivable event where foam may be accidentally or intentionally discharged. Complete and accurate inventories of foam and runoff containment supply should be on site, which may include pumps, hoses, sorbent materials, and containment structures. The foam environmental management plan should also include a survey of receptors and possible exposure routes on the site and surrounding lands, like nearby aquatic receiving environments or nearby drinking water wells. Essentially, those areas that will be the focus of environmental efforts should a release occur. So following a release, you're going to want to contain as much of the foam and impacted water as possible for treatment and disposal, with impacted runoff being directed to lined containment areas or vessels. To support environmental investigations immediately after the release, there should be photo documentation of areas where foam was deposited, and areas in the path of overland flow, and areas where foam and water were directed to. Drone aerial imagery is very helpful in this regard. For all events where foam is released, be that maintenance, training, or emergency response, it is recommended that a log be maintained that documents key pieces of information, including what products and volumes were discharged and how the foam and runoff was contained and disposed of. Excavation and containment of foam impacted media should also be completed as quickly as possible to prevent leaching to groundwater and partitioning to runoff. And water treatment systems are reasonably quick to coordinate as part of emergency response activities and can be effective at removal of select PFAS. However, long-term use of water treatment systems would require more detailed study to confirm that this option is the most cost-effective solution based on the range of PFAS present or likely to be present based on the degradation products of precursors over time. And in keeping with Health Canada guidance, testing of on-site or nearby drinking water wells in close proximity to the release site should immediately be initiated, with ongoing regular monitoring until releases have been contained, remediated, or risk assessed to confirm there's no potential health risks. So when considering the site assessment considerations, for environmental practitioners overseeing the assessment of PFAS impacted sites, as with all contaminated sites, the goal is to develop a strong conceptual site model to support remediation and or risk management. Developing an understanding of a meteorological, geological, hydrogeological, hydrological, and preferential pathways is critical to understanding the migration and fate of PFAS contamination. Given the mobility and persistence and potential for these chemicals to bioaccumulate, receptors that are significant distances removed from the source area should not be overlooked. Depending on the site and the surrounding land uses, the assessment of media quality at locations up gradient or upstream of the site should be considered given the pervasiveness of these chemicals in household, commercial, and industrial products. And when designing a sampling program, you should be familiar with industry standards or best management practices that will improve overall data reliability. There are some good guidance documents out there to consider, including those developed by the Interstate Technology Regulatory Council, by Transport Canada, and a guidance document developed by SLR for the Society of Contaminated Sites Approved Professionals of British Columbia. For the analysis and identification of PFAS, while there are thousands of PFAS in the environment, there are currently only lab standards for a few dozen PFAS. There are some novel services that labs will be providing in the nearest future to assist us with better understanding what we don't know. The assessment of total organic fluorine is one such tool that will allow us to roughly gauge what proportion of organic fluorine is in a sample that is associated with the known PFAS versus PFAS for which no lab standards are currently available. And without putting him on the spot, my guess is that Terry Obo, who is presenting a little later, might be willing to speak to some of these new PFAS analyses that BVL is developing or soon to unveil.
For sure.
Great. When planning for remediation or risk assessment, while there are many remedial technologies being trialed, the two approaches that are most commonly employed include engineered containment of both impacted material or excavation and offsite disposal for incineration. Both of these are quite costly ventures. For the offsite disposal option, you want to be sure that the facility that is taking the waste can actually handle it, and then that you're not simply creating an environmental issue elsewhere. And on that note, you may need to involve regulators in the process, as PFAS may not be regulated in your jurisdiction or because approvals are required for remediation. And risk managing contaminated material is also subject to uncertainties associated with the evolving realm of PFAS analytical tools and the limitations associated with our understanding of toxicity effects to humans and ecological receptors. So that brings me to the end of my talk. I hope that I've given those that work in industries where these products are used some food for thought. I'm able to take some questions now, and I also encourage listeners to reach out if there are any topics mentioned that they'd like to discuss further.
Thanks, Matt.
Yeah, thanks, Sarah. And if radio silence persists, I have another point. Maybe I'll speak to it now because it looks like I do have a few more minutes. That during our April webinar, someone asked if we had heard of foams being used on at landfills to suppress dust. And at the time, we did not hear that. It was a little bit concerning given that landfills were one of the areas that were known to have PFAS in the leachate. So we did a little bit of digging there and we reached out to a few suppliers. And based on the information we received, there's no indication that these products contain PFAS. So that's a good news story. But that kind of raises a very kind of good point that if you're using any product ultimately that's getting released to the environment, you need to do your due diligence to verify that you know what it contains and whatnot. So yeah.
Makes sense. Yeah, thank you. We do have a question here from Harriet. The question is, what is the most common disposal method of unused foam?
That's a great question. We haven't specifically had to deal with unused foam directly, I do not believe, but I would assume it would be kind of going the incineration route. In terms of like destruction or disposal, PFAS ultimately has to be destroyed, and there's many novel kind of remedial technologies out there, but so far kind of incineration is the most widely used, and incineration at temperatures above 1200 degrees Celsius. So that's really the trick for anyone trying to dispose of materials, is that you really need to nail down a facility that can handle these materials and that kind of has some environmental management procedures in place to make sure that so you can make sure that they're doing everything in their power that to not create a contaminated site elsewhere. So
great, thank you.
Yeah.
Sorry, just one second. I think that's all the questions that we have here.
Okay.
Joe, do you see any other ones there?
Nope, that's it for questions.
Great.
Just Matt, just to follow up to that, someone suggested like the Swan Hills incinerator would be a place that it would PFAS would be sent, right?
Yeah, that's certainly one of the facilities out there. I think you have to really follow up with Swan Hills and or other facilities that you're considering to kind of give them a full rundown of what you're looking at disposing and verify, not just that they can take it, but to really look into what they're doing and all these facilities, if the facility can actually handle it. But yeah, very good point with regards to Swan Hills.
Yeah, Swan Hills is one, and the other is what you're seeing a lot of development is mobile incinerators now, because we're the fixed incinerators we're decommissioning more than we're building, but there are now a number of suppliers that are offering mobile incineration services.
Yeah.
Right. On the line, that's Terry with Bureau Veritas that just spoke. So thanks for that, Terry, and thanks, Matt. I'll turn it back to Zara.
Thanks, Joe. All right, sounds good. Well, it seems like we are done with the questions. So thanks again, Matt. Really appreciate you speaking. We can probably move on to our next presenter. Our next presenter is Sandy Britt, QED Environmental Systems. I'm just going to switch it over to Sandy here. And Sandy, if you could.
Thank you so much. Yeah.
Thank you. Go ahead.
All right. Happy to do that. Matt, that was really a good presentation, and it's helpful to have some background on that as a way to start. I'm going to focus in on something that's much more specific, looking at groundwater sampling equipment. These sites that have these PFAS releases often have groundwater monitoring associated with them, determining where plumes are going and so forth. The trouble for equipment manufacturers is that many sampling equipment choices for materials include Teflon. Teflon has been thought of as this miracle material for us in the groundwater monitoring equipment manufacturer space, I guess. And so I'm going to talk about those those problems that we run through. I think that it's a tough nut to crack, but I think we've gotten most of the way there in terms of finding alternative materials that can be used for PFAS sampling in groundwater. My background is I used to be a consultant in the U.S. and California. I actually invented the SNAP sampler, passive groundwater sampling device. Had a company on my own for a while that was picked up by QED about 2 years ago. QED, and you may know, was one of the companies on the forefront of low flow groundwater sampling conversion from sample volume collection. And so when they picked up the SNAP sampler device, that was them moving into a passive mode. I want to talk a little bit about Teflon. Teflon is really sort of one of the best materials for sampling equipment. It's used in pumps and sometimes in balers, tubing, and other components that are often used because they're so nice, and the reasons that they're nice is because they're chemically inert, pretty non-reactive. They don't sorb contaminants, so oftentimes that's a nice feature when you have dedicated equipment with dedicated tubing. They have low gas permeability. They're temperature resistant, can work at very high pressure. So bladders that might be hundreds of feet deep can operate in for long periods of time, and they last a long time. Flex properties are really nice. So a bladder pump in particular is nice because that gets used thousands and thousands of cycles. And the way to make those last any length of time, you need to have a material that's really tough. Teflon fits that bill and had for 30 plus years. When the PFAS concern came around, there was a lot of scramble to try to figure out what would be the alternatives. The concern is that with many of the Teflon components, they're made from these fluoropolymers like PTFE and ETFE and FEP might be some of the names that you might recognize, and it's possible that they can result in sample contamination. I want to say early on that I think that concern is a little bit overrated. We have tested most of our components and not found PFAS leaching from most of them, but because the regulatory environment has been pretty conservative about it, oftentimes they've recommended the complete avoidance of the use of fluoropolymers. Anything that includes fluoro basically is taken off the usable list. Now, that's not always true, and I'll go through a couple of examples where guidance specifically prohibits it, but also allows a tested component to be used. But this approach, the prohibition of use of any kind of fluoropolymer is based on an abundance of caution, and research continues. It's really something that is not completely established yet, and new materials that contain PFAS are kind of being discovered all the time. Sometimes it's an anecdote. I've heard one story about aluminum foil having PFAS come from it, but it might be a specific manufacturer. But that's not something that you would naturally think of as being a PFAS contamination source. But I think the lesson that comes out of that is really you just have to pay attention and consider any of the possible choices. But for an equipment manufacturer, we're challenged with that. Finding alternative materials. A bladder, for example, and a bladder pump is particularly difficult to replace just because of the nice functional qualities of Teflon itself. So some examples of research and guidance that exists out there, oftentimes PFAS documents will, regulatory guidance will prohibit the use of Teflon containing or fluoropolymer containing components at all, even if it's suspected. So you don't want to go anywhere near the site if you have anything with Teflon, and oftentimes field sampling plans will say that you can't have food packaging or bug repellent and a number of different things that, and some of them are pretty strong. No Gore-Tex materials, Canada Gore-Tex boots and things. Not sure how many samples get poured over boots on the way to their sample container, but apparently just having it in the proximity is a concern. So the conservative guidance is designed to avoid any of those materials. This is another example, NGWA, National Groundwater Association, described in their field sampling analysis plan that anything that has PTFE or ETFE should be removed to the maximum extent practicable. And these go on. There's guidance that comes from the California State Water Quality Control Board that came out last year and effectively prohibits the use of many fluoropolymers. And and it says here that including but not limited to is kind of a typical thing to say. That PTFE, also different trademarks that include Teflon, so that's a Chemours trademark. Hostaflon, I'm not sure who owns that one, but PVDF, Kynar, that's another thermoplastic that can have that potentially could leach PFAS. A handful of other different ones, PCTFE, ETFE, FEP. Oftentimes these are listed. What's interesting is this last one with LDPE. It's really hard to remove LDPE from a sampling program, and there's so many things that either equipment is wrapped in LDPE, Ziploc sample containers are LDPE. It's really kind of a tough one to completely remove. But this California document, usually they're pretty forward-looking, as one of the big documents that have come out that recommend complete avoidance of Teflon at all. Tough one to beat. So what options are there for people who need to sample PFAS and avoid most of these Teflon components? Well, there are different materials that can be used, but all of them have some limitations as well. HDPE is a tough material, but it's not quite as flexible as PTFE and FEP. Life cycle testing on bladders, for example, for a bladder pump, show failures in a few thousand cycles, as opposed which is equivalent to a year or two of use in the field, as opposed to PTFE pumps that last for I don't think anybody's done it for 100 years, but I think QED actually has bladder pumps that have been in the field for 35. So 35 years with the same bladder, still functional. It's a pretty tough material. Polypropylene is not a great substitute. It's pretty inflexible. It's brittle in cold temperatures. It's not particularly good for, and it's tough to uncoil. It's really not particularly useful. Useful for sample bottles sometimes, but not for sampling equipment. Silicone rubber is pretty flexible, but it's problematic because it sorbs organic food really strongly. So for people who use peristaltic pumps, silicone rubber is often used, but usually in the shortest possible section of tubing possible, and that the downhole tubing might be HDPE, for example, a suction tube, lift tube, for peristaltic pump tubing. Vinyl is also a replacement for tubing. Alternatives to Viton. Viton is a fluoroelastomer, so rubber gaskets and O-rings sometimes are made of Viton, and they can leach organic compounds. They can, and there's a concern that they leach PFAS just because it has the fluorine in it. So replacing that is sometimes tough. Nitrile rubber doesn't last nearly as long, and sometimes can leach other compounds that are on a VOC analyte list. So there are particularly great options for Teflon replacement. The other question is whether there is actually PFAS in your Teflon. It's interesting that fluoropolymers tend not to leach PFAS actually. So PFA or PTFE don't necessarily leach. There are compounds or parts of things that are made from PTFE like Teflon tape that can leach PFAS, but it's not 100% of the time. So really the best way to know is to test. It's kind of the bottom line in most of these materials and compounds, is that you'd have to do some testing to see if they will work and see if they'll leach. And if they come out clean and you can be consistent, then that's a good sign. We've actually done testing of our own PTFE pump bladders and Viton seals and haven't found PFAS leaching from these. And this is done over a number of years when the testing list has increased in size from 12 or 14 up to in the 20s, the number of compounds now. Things like manufacturers trying to replace tubing is pretty challenging. As I mentioned before, HDPE and LDPE tubing, silicone tubing have their downsides. So it's not really super easy to find replacements. Oftentimes HDPE tubing is used and will function most of the time. But sometimes those can also be an issue for sorption or sorption of organics, especially at low concentration levels. There was a reason that Teflon tubing was recommended, 20 or 30 years ago for sampling for low-level VOCs, and that sorption question now is raising its head as people try to avoid Teflon. Dedicated sampling pumps and equipment can be made PFAS-free and Teflon-free. Sometimes there's some compromises. So here are some examples of articles that describe possibility of having leaching PFAS. This one that's highlighted here said thread seal tapes. So Teflon tapes, sometimes you can get some PFAS that leaches from them. That's just an example of one. Peristaltic pumps are a sampling method that is commonly used in locations where there's shallow groundwater. They can fit in any well, so diameter, oftentimes that's nice for direct push wells that might only be ½ inch or 3/4 inch diameter. Suction lift is used. Usually you're using some kind of silicone tubing for the pump head, and what we can do to avoid the use of fluoropolymers is to use either an HDPE or LDPE tubing as a suction lift and the discharge end. But peristaltic pumps aren't perfect. There have been problems raised about gas lift and having a negative pressure removing VOCs from the pump stream, but it is a way to avoid PFAS components. So that's one way, is to use a pump system like a peristaltic pump. Electric submersible pumps, that's kind of a mixed bag. Oftentimes the submersible pumps have small Teflon components. They have seals, motor seals, and wear parts that are PTFE, for example. And so you have to be concerned about that. And interestingly too, things like a Grundfos pump that has a electric line that goes down to the motor itself, the line itself actually has a ETFE coated cable, and that QED has found that actually leaches PFAS. So it's not the pump itself, but it's the wire line that goes down to the pump. And because that wire line is adjacent to the intake to the pump, then sometimes you can get low-level hits associated with that. So testing PFAS from the pump itself has shown it's clean, but oftentimes things that you wouldn't necessarily think of, like the wire line that goes to it, could be contaminated. So electric pumping is one option. You just have to, I think that the takeaway, the bottom line is you have to pay attention to what's actually in the components that you're using. Here's an example of a ETFE tubing in a soak test. I found pretty high result there for PFBA, and so that's that's just, tubing that you just have to pay attention to. It's a fluorinated tubing, so it would be something you'd be suspect of. So if you use materials like that, then you'd want to make sure you do your equipment blank testing ahead of actually collecting samples in the field. Bladder pumps. Bladder pumps are really a main product for QED, and we've been making them for quite a long time. We have PVC and stainless versions. Most of the ones that exist, or the ones that have been built in the past, are all use a Teflon bladder. The designs are pretty round and robust. You can have long tubing or long bladders that will pump 1/2 liter per cycle, and or very small, narrow and short ones to deal with short water columns or small diameter wells. Sampling depths can be quite deep, 1,000 feet, and even deeper if you use a drop tube. It's a wide range of material choices: PVC, stainless steel, to match water quality requirements. There are portable pumps that use either HDP or LDP bladders, but there's very few moving parts in these, so they're pretty long lasting, and they also can be made without Teflon containing components. So the Sample Pro pump has always been PTFE free or Teflon free, so it's a really strong go-to. Oftentimes people using a portable sampling method to collect samples for PFAS. This is a very commonly used device. QED has developed our dedicated pumps. We've developed a proprietary bladder that is PFAS free, and it's been tested and certified to be PFAS free, so that works. Our warranty is a little shorter for this for that alternate material, but we found that it works nearly as well as the Teflon bladder. So we have two different products, the Zero and the Clear. The Clear has just been tested, so they're tested to show that they're PFAS free. So the Clear actually uses the PTFE bladder, and we certify that as Teflon or as PFAS free. And so depending on your individual circumstance, whether your regulatory jurisdiction requires no Teflon, you can use the Zero sampler or well wizard pump, or if you are allowed to use Teflon components that have been shown to be clean, then you can use the Clear version, which is essentially the same as our original. The only thing that's different is that it doesn't have Teflon tape, for example, for thread seals. All right, so and I guess there I just popped up the available. It's been available since late last year. There are also passive and no purge samplers out there that are sometimes used for PFAS sampling. Passive samplers, you may be more familiar with them, heard of polyethylene diffusion bag samplers. Unfortunately, those don't work for PFAS because the PFAS does not transfer through the polyethylene membrane. So you do need to use some kind of grab type sampler. A snap sampler is one of those devices. The snap sampler was originally designed with Teflon components. In fact, this picture here shows those end caps with the two little holes in them. That's PFA. And that was selected because of VOC sampling and other sampling that is benefited by using Teflon. There's also a spring inside the bottle that connects those two end caps that is Teflon coated stainless. So the original snap sampler was not PFAS free, but that's also been altered to allow it to be completely PFAS free or zero. The snap caps have been changed to an acetal, which Delrin is another name for that. So the snap caps have been replaced, and then the Viton O-ring is EPDM now. So and the spring is no longer coated, so it's just a passivated stainless steel spring. So the bottles are a little bit different. There's also a different type of cap and liner that's been tested to be clean, and so so both of these, either sampling for PFAS or sampling for other analytes within the well that you're also sampling for PFAS, all the equipment that goes down hole can be PFAS free. So again, that came out late last year. So what we try to recommend then is to kind of follow a common sense approach and look at the materials you're going to use. Look at studies of others who have done work on PFAS content in materials. To the extent that we can, we have replaced them or tested everything that we think might be a potential concern. And you know, we have eliminated those suspect materials, but that's also going to be on you to look for and test those materials where you need to. For dedicated pumping systems or passive samplers, you can do equipment blank testing to make sure that they're PFAS free. We certify it, but it's always better to have your own equipment blank results to prove it to yourself or your regulator that the material, the equipment that you're using is truly PFAS free. For existing, if you happen to have existing dedicated systems, for example, well wizard pumps that are already deployed in wells, they should be clean. But the thing to do is just collect samples from them. And if it turns out that they are clean, then that's a double proof. It proves that the pump is clean, it also proves that your formation is clean. If you do get a hit, then it's probably worthwhile to pull that pump and do that sampling again with a different pumping system that you know is completely Teflon free, and then that will be your determination of whether formation is the source. So it's pretty straightforward to try to avoid Teflon where you can, and at least we have come up with some different solutions that you can try to fit the bill in that case. Okay, so I'm just gonna wrap up right there. Questions if you have them. Again, my contact information is here if you think of questions after the show, and we'll go from there.
Sandy, can you repeat your last couple of lines? We lost your mic.
Oh, I'm sorry. Can you hear me okay now?
Sure can.
Yeah. Okay. Yeah, I was just saying that if anybody had questions, this is my contact information. So you can ask questions now, or if you think of something later, then by all means you can get.
Thank you, Sandy. We have a question here. It's from Rafael Jerez. I'm just going to read it here. The Teflon-free alternative materials you covered are good for tubing and pumps. Are there any such materials for Teflon-lined septa for capping the groundwater sample vessels for organic contaminant analysis?
Yeah, that's a tough one because usually a septa cap has got a silicone septum with a Teflon liner, right? And that's usually used for VOC containers. If you're going to use a septa for a PFAS sample, usually that has an HDPE liner. So you've just got a hard HDPE cap, and either it has no liner or it's got an HDPE cap. Your lab should probably be able to advise you of what materials to use. Typically, the cap that needs to be Teflon, so for a VOC cap, you're not going to also be testing for PFAS from that actual container. So you have to be a little bit careful and not to, roll that septic cap around and put it on one bottle or the wrong bottle or something, so that you commingle them. But it's one of those things that you'll just have to be a little bit careful of. But the lab should be able to help you pick the right containers for your analysis.
Yeah, I can weigh on that, being a representative of labs. Yeah, when it comes to PFAS sampling, these are unique containers. They're separate from all other containers, and typically they're 125 mil, either polypropylene or high density polyethylene with no liner. There's no Teflon liner, and these are typically sample containers that are proofed by the lab, that the lab can certify that they are PFAS free. Similar, Sandy, to what you're talking about with a lot of the materials that you're going to find on site. if you proof them and demonstrate that they're PFAS free. So the silicon septa, as Sandy has said, with the Teflon liner or the Teflon inside, it's a non-issue, unless, as he said, unless you start migrating it from one container to the next, which just, it doesn't make sense.
Thanks, Terry. So for everyone that maybe didn't see or hear this, that was Terry Ogle from Bureau Veritas. He's one of our speakers on this session. Doesn't look like we have any other questions. Shall we maybe Joe, shall we just move on to the next presenter then?
Yeah, definitely.
Okay, excellent. Let me just switch the screen here. There we go. So, hi, Terry. Our next presenter here is Terry Ogle from Bureau Veritas Laboratories. Terry, if you could introduce yourself, maybe a sentence or two before you present, that would be great. Thank you.
Great. Good afternoon, everybody. My name's Terry Ogle, and my role is Chief Science Advisor at Bureau Veritas Laboratories. I've been doing this for, let's say, a long time. Working in the environmental sector with a pedigree that spans both the consulting world and the laboratory industry. So my role is pretty much well, I was going to say the old guy, but the science guy. My job is to ensure that the value of science and good science is brought to our customers, be it in the private sector, the public sector, and the public in general. I'd like to start my presentation by certainly by thanking ESAA and in particular Joe Chwanek for putting this together. I would much rather see people face to face, but we're living in extraordinary times right now, and the requirement for physical distancing, lack of travel, etc., which is going to be around just for a little bit. This is certainly a good alternative, and I very much appreciate the effort, Joe, that you've put into this, and ESAA. So I thank you for the opportunity to present.
Thanks, Terry. Thank you so much for that.
So the presentation I'm going to talk about here, this is I'm going to talk about PFAS replacement compounds. Over the years, I mean, PFAS, many have said that, I've said it as well. We refer to them as emerging compounds. They're not emerging compounds. We've known about them for a long time. They're compounds of emerging environmental concern. And 10, 15 years ago, when they really were starting to grow legs, as it were, in terms of visibility and concern, a lot of the companies started to phase them out. But the properties that they introduced into a lot of the materials that we use, the beneficial properties, they still wanted to keep them. So they started coming up with replacements. And some of those replacements are just as much of a concern as the compounds that they replaced. So what I'm going to talk about here are some of these replacement compounds. I've referred to them as the next generation. So I will give a quick review. I mean, everybody, we all talk about PFAS because they're really interesting compounds. They have certainly exploded in terms of interest, public awareness, and the level of effort being put into the characterization of these compounds, the delineation of these compounds on site. just a whole bunch of things, and I commend both Matt and Sandy. Those were excellent presentations. I very much appreciated them. I'll talk a little bit about the replacement compounds themselves, and kind of look at the question, why do we care, or should we care? Then I'll talk a little bit about the sampling and analysis. I may cover some of the material that Sandy and Matt have already covered, and then talk a little bit about regulatory standards. So when we think of PFAS, the general concepts, everybody's heard this. I won't go through it in detail, but they're man-made compounds. I say it's greater than 3,000. Matt has got updated numbers from some of the work that Jennifer Field has done, and we actually had this compound about, identifying the non-target compounds. The issue with them is they're ubiquitous. They're everywhere. And, up until now, the compounds receiving the most attention have been PFOS and PFOA, perfluorooctane sulfonic acid and perfluorooctanoic acid, the sulfonate, or the sulfonate and the carboxylate. And after those, kind of the next most studied compounds have been the C6, the perfluorohexane sulfonic acid, and the C9, perfluorononanoic acid. And included, I guess, as part of the replacement compounds would be PFBS, the C4 sulfonic acid, perfluorobutane sulfonic acid. But the real up-and-comers are the shorter chain PFAS, the C4 and less are being used more and more as replacement compounds. And so I'll speak to one of them is GenX. You've heard about the physical properties. These are, they're super persistent. They don't degrade, for lack of a better term, from a romantic standpoint, they're calling them forever chemicals. They do degrade, but it's really, really slow. And more so in some cases, they transform. But the fact is that the carbon-fluorine bond is a very strong bond. It's one of the strongest atomic bonds, and these things just don't break down. And that's really what the advantage is to these compounds and incorporating these compounds in materials like Teflon or the AFFFs that Matt referred to. They don't break down. They put out a fire by smothering it. They're low volatile. They're not very volatile. They're very water soluble. That makes them a little bit challenging when it comes to analyses. But one of the things to consider from a sampling standpoint is that they absorb to a variety of materials, and it's hard to predict the partitioning given the different compounds and the different behaviors of each compound. So they do bioaccumulate, as was mentioned earlier, but they don't bioaccumulate in the sense of things like organochlorine pesticides that tend to accumulate in the fatty tissues of the body. The bioaccumulation for PFAS is more the protein-rich organs in the body. So you're going to find them in blood, you're going to find them in the liver, that sort of thing. And as I said before, some of them can degrade or transform into other PFAS. So this is where you start talking about the concepts of precursors and end products. Just some conventions that everybody's heard. PFAS is an umbrella term that includes both per and polyfluorinated compound. Matt had a slide that showed you the differences between a perfluorinated and a polyfluorinated compound. It is a plural noun. There are no PFASs. It is PFAS. It's like moose, right? PFAS. So the trend is, going forward, the trend is to report sulfonates as well as the sulfonic acid. This is more now the convention. Starting off, everybody referred to PFOS as perfluorooctane sulfonate. But in trying to harmonize and standardize the nomenclature, the agreement is really to go with the protonated form rather than the conjugate. So it's the perfluorooctane sulfonic acid. Perfluorinated, as Matt said, all of the carbons have fluorine hanging off of them. Polyfluorinated, not all of the carbons have fluorine on it, and these are often the precursor compounds. So The current target compounds talked about perfluorooctanoic acid and perfluorooctane sulfonic acid. But as was shown, there are different types. These are C8 versions. These are the ones that kind of kick things off. I have identified Teflon and Scotchgard. Let me be clear. This is not Teflon and this is not Scotchgard. Okay, Teflon and Scotchgard are polymeric materials that could contain hundreds or thousands of different compounds with different chain lengths, and the formulation is what gives Teflon its unique properties, or Scotchgard its unique properties. But it was a way many years ago to relate to PFOS and PFOA. So after the end compounds, people start just by part of the when it comes to the unique behavioral characteristics of some of these compounds is they have a hydrophobic and a hydrophilic end. Okay, they're surfactants. It's one end likes water, the other end not so much. So they're used to repel water or repel oil in different formulations. But these are like I say, the two that kicked it off. Then they started looking at precursor compounds, and now you're getting a little bit more complex in terms of the molecular structures, and certainly a lot more complex in terms of the nomenclature. So this is where the acronyms start becoming helpful, and the acronyms, the conventions are consistent across the board. But when you look at the 6,2-fluorotelomere sulfonate. That is an example of a polyfluorinated alkyl substance, and as you heard earlier, it's a common ingredient in the older aqueous film-forming foams. So why the need for replacement compounds? And there certainly has been advancement in the understanding, but really back in the day, in 2010, the global suppliers of perfluorinated compounds, actually perfluorooctanoic acid, they agreed to a 95% reduction in PFOA and related precursor levels in emissions relative to the 2000 levels, and they agreed to the total elimination of PFOA and its precursors in emissions, beyond 2015. There's also in the U.S. what's called the significant new use rules, and these are relating to PFOS and PFOA, where you have to be very cognizant and careful, and in some cases not use PFOS and PFOA moving forward. And it's somewhat similar to the risk management plan that was published by Environment Canada many years ago, which basically seeks to have the same thing, to ensure that the PFOS concentration are as low as possible, prevent reintroduction of this compound into the market, and it addresses sort of the remaining uses of PFOS. So when we talk about AFFFs back in 2013, that it was mandated that AFFFs moving forward could not contain more than a half a part per million, so 500 parts per billion of PFOS. And what we've seen as a laboratory in analyzing just a whole bunch of AFFFs over the years is that it's pretty much held true. So the risk management strategy in plain English to me is similar to the significant new use rules. Is basically the regulators are saying that yep, we know we have a problem. Let's not add to it. And so the other with the AFFFs having a half part per million limit, having been in the industry a long time, my first question is, what'd you replace it with? And this is where you start looking at C6, the perfluorohexane sulfonic acid, has skyrocketed in some formulations. So it's interesting to see how things go with the fluorine-free AFFFs. So the replacement compounds, you're basically going from the long chain PFAS to the shorter chain PFAS. So the longer chain is greater than 7 carbons. So PFOA and PFOS have 8 carbons. Perfluorohectanoic acid or heptanoic acid and perfluoroheptane sulfonic acid, same thing, only 7 carbons. Anything C7, C8, C9 would be the nonanoic acid, etc. Have always been viewed as being more problematic than the shorter chain PFAS. So this is less than C6. And this is where you start getting into some of the replacement compounds, where not only are there fewer carbons, but they're introducing oxygen into the chain. So they become ethers and polyethers. The suggestion being that these compounds are less of a hazard to human health. So they pose less of a risk to the environment and to humans. So the PFAS replacement compounds, these are, again, I'm going to make chemists out of all of you. And if you really want to impress friends, say this kind of stuff in a bar. But the point here is, when we talk about Gen X refers to a process that is used as an aid to formulating and manufacturing Teflon, PFTE. But it's become convention to use the term Gen X to refer to this compound, the 2,3,3,3 tetrafluoro-2-heptafluoropropoxy propionic acid. So one way of looking at that is HFPO or HFPD. It's the diacid. There's another acronym for it, but actually the fellow who identified this compound was from the EPA, a guy named Mark Striner. And you know, when it came to referring to it as Gen X, that was in fact his comment was Gen X rolls off the tongue a whole lot easier than this big long compound that I've presented. But Gen X is one of the replacement compounds that is getting a lot of attention moving forward. Another is Adana. I'll speak to these compounds shortly, but same thing, only it's a diether. You can see the 2 oxygens in the carbon chain. And then one that is getting interest, and sometimes I wonder why, is this compound is referred to as F53B. It's been used extensively in China in the electroplating industry. And the other thing that you know is notable is the introduction of a chlorine atom into the chain. But these are really the key replacement compounds that are garnering a lot of interest in the environmental industry. When we talk about Gen X and Adana, they're pretty much used for the same purpose. The Gen X was manufactured by Chemours, and everybody's heard Chemours is just a spin-off company of DuPont. Adana is not the same compound, but pretty much for the same purpose, manufactured by 3M. And what these are is they're processing aids for manufacturing Teflon, among other fluoropolymers. So processing aids in the polymerization of polytetrafluoroethylene, among other fluoropolymers. Like I say, in English, that just means they're trade names for man-made chemicals used in manufacturing nonstick coatings. The thing to consider is they're used on their own, but they are also potential byproducts produced in other processes. And so if a plant is manufacturing Gen X or Adana, or rather if they're manufacturing other PFAS or PFAS related materials, then these compounds as byproducts, they weren't looking for them. They may not have even known they were being made. They could have been introduced in the environment well before they started being used as a replacement compound. Gen X is particularly notorious because it's getting a lot of press because of ongoing releases in the Cape Fear River. from the Chemours facility in Fayetteville, North Carolina. So the Cape Fear River between Fayetteville and Williamsville, or I forget, but downstream in North Carolina, there's a great deal of concern because of Gen X. The levels, they recognize the levels are going down, but it's still there. So Gen X and Adana, they're probably more likely to be detected in water where the fluoropolymers are being manufactured. And probably less likely to be detected where chemicals containing PFAS are actually being used. F53B is an interesting one. F53B is it's actually it's a trade name for a 6,2 chlorinated polyfluorinated ether sulfonate. It was used as an alternative to PFAS, and it was used in the electroplating industry. And so in those industries, it was detected often and frequently. So wastewater from chrome plating industries usually contains high concentrations of PFAS and or F53B. The thing that is notable is F53B has been used almost exclusively in China. Since the 1970s, and so the question is, why the interest here? Well, we have some clients that they have specifically requested F53B. So it's included in the suite of replacement compounds that we will test for, and I'm sure others will test for, because there is a concern that of potential impacts in North America. So why should we care? These replacement compounds, they have been marketed by their manufacturers that because they're a lower molecular weight, that they're going to be less persistent, less bioaccumulative, and exert a decreased toxic effect. If they're a lower molecular weight, they're typically more soluble, and so the suggestion is that they're not going to accumulate in the body; they're going to be excreted or removed from the body at a faster rate than the higher molecular weight compounds. Again, long chain PFAS versus short chain PFAS, but the emerging evidence, it appears to suggest, as I've said, not so much. PFAS replacements are persistent. They do tend to bioaccumulate in a similar fashion to their higher molecular weight compounds that they're replacing. And the toxicity information is limited. It is being suggested that Gen X and replacement compounds are equally, if not more toxic than PFOA, the compound they're replacing. But then I look at it from a practical perspective as well. The lower molecular weight compounds are more soluble in water. It's been shown from different treatment processes. If you're treating a groundwater system, one of the most common approaches is to pump and treat. You're typically passing the water through granular activated carbon. It's harder to remove those lower molecular weight PFAS from water. That's why a lot of treatment systems now are incorporating an ion exchange resin after the activated carbon, because the lower molecular weight compounds aren't being trapped, and you have to take a more aggressive approach. But like I say, from a practical standpoint, I figure if it has increased solubility, it has increased mobility. So where the higher molecular weight compounds may be more hazardous, which ones pose a greater risk? This is what keeps me up at night. Is that the lower molecular weight compounds, while they may not be as toxic, there is increasing evidence that there is a potential health effect, and they're more mobile. So they're going to travel further and more readily than the higher molecular weight compounds. And I think Matt had a slide where he showed a plume. And the lower molecular weight compounds like the PFBS were taking a different path. Field sampling, as was shown in the earlier presentations, you really have to maintain a great deal of rigor with the sampling protocols. The sampling, the field quality assurance plans, they have to address the potential for cross-contamination. This speaks to the ubiquity of these compounds in different materials. As Sandy was saying, Teflon, is Teflon a real contributor? We have looked at Teflon as well. We have tested it, we have leached it, we have digested it, we have extracted it, and we're not seeing any real impact from Teflon liners. But there's just a plethora of other materials that may contain fluorinated compounds that you'd have to be sensitive to in developing your field sampling plans. With respect to the Teflon as well, while QED and Bureau Veritas, we've not seen much impact from Teflon, you have to recognize as well the levels that we're measuring are at the low part per trillion, and in some cases below the part per trillion level. And if you have Teflon in your sampling regime and you start seeing consistent hits of PFAS at trace levels in your compounds, or in your samples, can you say unequivocally that the PFAS did not come from the Teflon? So as was stated earlier, and I concur, is avoid it. Just if you can, avoid Teflon in the sampling protocols. But the other is that PFAS absorbs onto surfaces. And this is something that we recognized many years ago. And different compounds will absorb at different rates, but the fact when you're collecting samples, and this goes for both the replacement compounds and the standard list of compounds, and I use that term standard loosely because the list is dynamic, it keeps changing, but the surface to volume ratio is important to consider. So if you're collecting a 125 mil sample of water for PFAS, to consider that fill the bottle up, because the relative impact is much less if you fill the bottle versus only partially filling it. Minimize transfer of samples from container to containers. The water for the blanks, ensure that it's PFAS-free. Laboratories will supply PFAS-free water that, if need be, can be certified. That we can provide a certificate of analysis saying that the water is PFAS-free. And the same thing with the sample containers. But it's important to discuss with the laboratory, have a close relationship with the laboratory. But as was said earlier, be sure there is no substitute for a solid and defensible quality assurance program. When it comes to equipment decontamination, again, the rinse of the equipment with PFAS-free water and submitting blanks is very important. The analytical method, I won't spend a lot of time on the analytical methods, but the laboratory industry as a whole has pretty much focused in and zeroed in on what I'll call industry accepted best practices. And for the analysis of water, look for US EPA method 537 and more recently method 533. With 537, most laboratories will say it's a modified 537. This is a method that was established by the EPA for drinking water. And editorial comment here, probably not the best method for these compounds, but it is what it is, and that's why 533 has come around, and more and more labs are implementing 533. The number of compounds being tested is about 50% higher. Right, you're measuring 18 compounds in 537. It's 29 now in 533, but it is a weak anion exchange extraction of the water, and then its analysis using isotope dilution, liquid chromatography with tandem mass spectrometry. Soil methods are typically based on a ASTM method. There is a draft protocol for solid and liquid waste coming from the EPA. It has its weaknesses, but it's still in draft form. But again, the fundamental or the important component is the analysis by liquid chromatography with tandem mass spectrometry. It's become de rigueur and as I said, accepted as an industry best practice. Isotope dilution is also it's something that's done in the laboratory to compensate for things like adsorption of the compounds onto walls of containers, etc. And there's certainly not blank contamination or correction. There's no need for it if you're analyzing using this technique, isotope dilution. When it comes to reporting these compounds, typical reporting limits for anything from PFBS to GenX to Adana, they're at the same levels as the other standard target compounds in PFAS analyses. Typical reporting limits are anywhere from 20 to 40 parts per trillion. So what micrograms per liter is parts per billion, 0.02 is 20 parts per trillion. And I always put that into perspective using the analogy of time, where a part per billion is 1 second out of a billion seconds, which is 1 second out of 31.7 years. So when we talk about 20 parts per trillion, that's 20 seconds out of 32,000 years, right? It's 3 orders of magnitude lower than 20 parts per billion. So it's important to recognize the levels that the laboratories are measuring at, because this speaks directly to the need for rigor in the sampling protocols and the materials that are used on site. There are low-level methods that get you down at the low parts per trillion, and as you can see, the method detection limit is subpart per trillion. The difference between a method detection and a reporting limit is a method detection limit, a laboratory, it's a statistically derived value based on replicate analysis of the ideal sample. It's typically laboratory reagent water that's spiked at a known concentration. It is analyzed from start to finish 8 times, measure the standard deviation, multiply by a student t-value that gives you a 99% confidence interval, bam, you've got a method detection limit. So if you've got a really, really precise test, you're going to have an unrealistically low method detection limit. That's why laboratories typically report a reporting detection limit. So where a method detection limit is you're 99% sure my response is something different from 0, a reporting detection limit is, yeah, I'm sure it's something different from 0, but I'm also confident in the number that I'm measuring at that range. From a regulatory standpoint, the regulations, more and more jurisdictions are migrating from guidance values to regulatory limits. So perfluorobutane sulfonate, British Columbia, just by the way, and to Matt's point earlier, is still, as far as I know, the only jurisdiction in Canada that actually regulates PFAS, at least 3 compounds in different situations. But as you can see, these are the types of values. Minnesota as well is incorporated PFBS. GenX, North Carolina, and for obvious reasons, Cape Fear River is in North Carolina, is looking at regulating GenX at 140 parts per trillion. I always throw this one in. This is perfluorononanoic acid. Health Canada. It's actually an order of magnitude lower than many of the other target compounds. So the question is why, and is this something that we need to be keeping an eye on moving forward? So in summary, when it comes to PFAS replacements, GenX and Adana are a growing concern in North America, as can be seen by the interest in a lot of the stakeholders. These are clients of ours, by the regulators. F53B, it depends on how extensively it was used in the North American marketplace. Like I say, if it's suggested that it's used uniquely in Chinese electroplating facilities, well, down south of the border, the US DoD is still focusing attention on all three. Good sampling practices are a must, so pay attention to sources of contamination. Use PFAS-free water. Check PFAS-free water as a final rinse. If you are decontaminating your sampling equipment, just be sure that you rinse it after with PFAS-free water. And ensure that you have a solid field quality assurance program. Laboratory analyses are becoming increasingly complex as new compounds are being added to the list. As I said in my slide, it's greater than 3,000 compounds. New information that I got from Matt just now is 4,700 plus. So it makes it difficult for the laboratories as more and more compounds come out, because in order to quantify these compounds, we need to have standards. And some of them are isotopically labeled standards. So they are difficult and they're a limiting factor sometimes in our ability to test for different compounds. And one analysis may now be 2 or 3 injections on the instrumentation. And the other is, as I said before, what were once provisional guidance values are becoming regulated standards. So I do want to acknowledge some of the folks that I get to work with. Stephanie Paulin, many of you may know, she is our project manager, senior project manager, and her focus is on ultratrace analysis, which includes PFAS, it includes chlorinated dioxins and furans, PCB congeners, etc. Adam Robinson he's the guy who makes everything work. He supervises the liquid chromatography and LC-MS groups, and he's the one who really does all the work. I just get to present on it. That's me at the bottom. So you have contact information. If you do have any questions, we welcome them. We're always prepared to speak to you about PFAS, among other things. And I thank you for your attention.
Thank you so much, Terry. I think we're a little bit over time, so we're just going to hold any questions on this presentation, and we'll do questions after the next one, provided we have the time. So actually, Terry is doing another presentation here, and I'll let Terry introduce that one. Thanks, Terry.
Hi, my name's Terry Obo. I'm Chief Science Advisor at EnviroTech Laboratories. Redundant in the dictionary. Under redundant, it says C redundant. The next presentation, and again, I do appreciate the opportunity from ESA to present. In this case, this one is more of a general overview of PFAS. And I've titled it From PFOS to Gen X. It was really PFOS and PFOA that captured people's attention many years ago to Gen X, what we just talked about, some of the replacement compounds. So in this case here, I'll talk about PFAS as contaminants of environmental concern and just give a little bit of history. So this is a little bit lighter. What have we learned over the years from the standpoint of PFAS? And what is the future of PFAS in the environmental marketplace? I'll look at regulations, some of the analytical needs, and some market considerations for those who are engaged in PFAS characterization, remediation, treatment, etc. So I love this slide. When you think of PFAS, think it's an awesome photograph and really kind of frightening. But PFAS has been around, as I said, for many years. It was used as part of the Manhattan Project. It was they were having trouble with failing O-rings, rubber O-rings, and so they approached the folks at DuPont. It was EI DuPont at the time, and kind of asked, have you got a solution for us? And they said, well, maybe. this guy named Roy Plunkett, about 6 or 7 years earlier, by accident, discovered Teflon. And this is where you start getting Teflon O-rings. But it's just, I love history like that, little tidbits, fun facts. So as I said before, these are not new. We've known about them for a long time, but it's only as of the mid 90s that people started really taking an interest in this class of compounds because of their ubiquity and their potential risk to human health. So when you think PFAS, again, the non-stick fry pans, the food packaging, aluminum foil. Sandy, you brought up aluminum foil. Yeah, it's if you consider aluminum foil, to keep it from sticking, they would have a coating on one side. You know how you have a shiny side and a dull side? The suggestion was that the coating contained PFAS, and I think it was demonstrated in some analyses that Jennifer Field and Bill DiGiuseppe had done on different materials. And again, just another piece of useless information going back before PFAS. The suggestion was that PCBs oil may have been used. That's why back when I was a grad student, you had to always rinse your aluminum foil with an organic solvent so that there was no contribution. Things like Gore-Tex, same thing. If you go back, the PFAS is a surfactant. It repels oil, it repels water, so it's been incorporated into various fabrics. Scotchguard for protecting fabrics, and as everybody has heard, aqueous film-forming foams or firefighting foams. The environmental interest in PFAS, well, it started, as I said, with PFOA and PFOS, and I went the extra step and put these little curly equal signs. It's not Teflon, it's not Scotchguard, but that's how people would relate to these compounds. And then it grew. The target compound list grew to incorporate compounds in the C4 range up to the C14 range. Well, from there we got into precursors. And these are the fluorotelmer sulfonates, the fluorotelmer alcohols, sulfonamides. The names get longer and longer, as do the acronyms, which, just as an aside, poses problems for laboratory information management systems where you may be limited in the number of characters that you can use in naming compounds when you're reporting the results to clients. We just heard about replacement compounds, the Gen-X, the F53B, Adana. As I said before, PFBS is another example of a compound that is used as a replacement for the longer chain, higher molecular weight compounds. As I said, 3,000 plus compounds, so I'm safe, okay, for the 4,700. It has really grown in interest, and not only Jennifer Field, but Chris Higgins at the Colorado School of Mines. They are doing an awful lot of work using time-of-flight mass spectrometry, identifying new classes of PFAS, identifying compounds that are of concern. So this is an area that is not going to go away anytime soon. What are the major sources of PFAS impact? You've heard AFFF, not only the releases, but inventories. There are huge stockpiles of old AFFFs and that are used in firefighting training and response sites, etc. Industry itself, DuPont, as I said, or their spin-off company, Chemours, 3M. But then there are the third-party manufacturers who are buying materials from DuPont or 3M, for instance, and manufacturing their own products. Wastewater treatment plants, biosolids was brought up by Matt earlier, is an important area that we're certainly looking at. Landfills, historic impacts, and it's nice to know that the foams that were used for dust suppression are not PFAS containing, but the landfills are all over this right now because, you know, accepting materials for the last 50, 60, 70 years in certain landfills is this potentially a problem. And a landfill they are historically they're targets. That if there is PFAS contamination, there's a landfill nearby, immediately the thought is that, oh, it's the landfill. So they're very interested in where this is going. When it comes to toxicity, the toxicity studies are inconsistent and inconclusive. I mean, a lot of even the toxicologists are saying that the studies there's not a lot of harmonization and standardization in the protocols. But the studies, all of them are suggestive of PFAS toxicity. I don't know if anybody's really identified a direct cause and effect. As I said before, they bioaccumulate in the protein-rich organs. IARC has classified PFOA as a possibly carcinogenic, and EPA has concluded that PFOA and PFAS are possibly carcinogenic. What that means to me is if you look at all of the references, they link PFAS with different maladies, whether it's carcinogenicity or teratogenicity or genotoxicity, it is always associated with. And like I say, I'm not sure if anybody's really found a link, but the toxicologists all agree that there is a need for harmonization in the study protocols, and that significant additional research is required to conclusively link PFAS to cancer. What have we learned? Here's my boy again. The field sampler. From a sampling standpoint, you heard it all before, rigorous sampling protocols, etc. Why I call him my boy? I always present this photograph because anybody who's been in the field knows that nobody looks that good collecting samples in the field. So what have we learned? Now we're talking. This is what field sampling looks like. Through experience, a lot of the environmental stakeholders are adopting a more common sense approach, but still precautionary to materials on site. And this speaks directly to what Sandy was presenting earlier, that they are categorizing materials as some are prohibited, some are acceptable, and some need screening. So there are certain prohibited materials, waterproof field books. Why are they waterproof? Well, they probably contain PFAS and are potential sources of contamination. Now, remember again, you are analyzing at the low part per trillion level, so seconds in 32,000 years. Decon 90 is a detergent used for decontaminating field equipment. It is a known contributor of PFAS, so there are other acceptable detergents, Alkanox, Liquinox, Citrinox, and then there's some materials that, well, it may have had PFAS used in its manufacture, so have it tested. If you are not sure, talk to the laboratory, and we can run proofing studies to help determine if material that's being brought on site is a potential source of contamination. But it is certainly, it has come a long way from 6-7 years ago when the rule was do not shower 3 weeks before going out into the field, do not use this, do not use deodorants, etc. I think there's a more realistic, common sense, yet sensitive to the needs of the sampling program approach. What have we learned from an analysis standpoint? Eliminate all sources of contamination, all potential sources of contamination. Isotope dilution, as I said earlier, is a must. If you're not sure, just ask the lab. Are you using isotope dilution, liquid chromatography with tandem mass spectrometry, or isotope dilution LCM SMS? Typical reporting limits in water are 2 to 4 parts per trillion. Detection limits are subpart per trillion. Typical reporting limits in soil, it's still parts per billion, but soil is a little bit more challenging from an analytical perspective. The reporting requirements, is the laboratory reporting the branched or the linear isomers? A number of years ago, people started looking at PFOS, perfluorooctane sulfonic acid. It has 8 carbons. it can have different configurations. You can have branch and still C8. The PFAS that I presented to you is the linear isomer, but there are branched isomers that are still PFAS. And most technical mixes are going to be mixtures of the branched and linear isomers. Well, it's important to distinguish between the two because it impacts the calibration of the instrumentation, and you can see variability in the data by upwards of 50 to 80%. And recognize the naming conventions are more towards the not the conjugate, but the protonated form of the acid form. From an analytical standpoint, TOPS, the total organic or total oxidizable precursors assay, it is a way of predicting future liability. If you've remediated a site and you are getting non-detects on the target compound list, PFAS, are you sure that you've removed all PFAS? Remember, the laboratories are reporting anywhere from 14 to, we are up at 32 compounds. We'll be over 40 by Q3 because of the requirements of EPA 533. But out of a potential 4,700 compounds, a lot of the higher molecular weight compounds over time have been shown to transform into the end product. So where you think you've cleaned up PFAS and you've now filled in the site, built townhouses on the site, if there are precursor compounds that you weren't measuring before and they transform to PFAS, you have a future problem. So one way of addressing it was the total oxidizable precursors assay. It's not a panacea. It provides useful information, but you have to recognize some of the limitations. It's not necessarily a comprehensive indicator of total PFAS, and it's expensive. It doubles the price of your analysis and then some. From a remedial standpoint, somebody had talked about remediation. Where are we with remediation? Water, the most common is treatment using activated carbon, ion exchange, or sequestration. But basically, what you're trying to do is separate PFAS from the matrix, so you're not taking tankers of water to Swan Hills for high temperature incineration. So, like I say, I view it as a remediation. You're not getting rid of it. You're just repackaging PFAS into a more manageable form onto a solid matrix. But as you can see here, there are different approaches with different degrees of success, and I think it speaks to the frequency of its use. From a soil standpoint, remedial approaches are excavation, right? Because right now, and I think it was mentioned earlier in Matt's presentation, is high temperature incineration is the most effective approach to treating PFAS. So excavation is probably the methods that are most commonly used. Cap and contain, again, they're different approaches to repackaging and stabilizing the problem. It's still there, but the risk has been minimized. Regulations, I'll just go through this one quickly. You saw this. People are migrating from guidance values to genuine regulations. So where are we going? What are the needs in the future? Well, the laboratories, certainly what we're working on is the new matrices. It's not just water and soil, air. From a treatment standpoint, if incineration is the approach to treating the soil or the media that was used for the treatment of a contaminated groundwater, well, as soon as you burn something, somebody's going to want to know what's going up the stack. And there's a lot of questions around this. We are working on methods. I know the EPA through Jeff Ryan is they're working on methods, and I understand from a discussion I had the other day that they're looking at putting out a method for stack sampling for PFAS towards the end of the year, sometime in Q4. Biosolids. We've heard about biosolids. The PFAS that is getting into sewage treatment plants is not being treated, and because it absorbs onto solid matrices, biosolids are certainly of interest. Tissue, not just plants, but animals. There's still a lot of work being put into an effective, accurate, and precise method for analyzing tissues. New methods. Here you go, Matt. We talked about total organic fluorine, and certainly as a replacement for total oxidizable precursors. Total organic fluorine, what we're talking about here, and I refer to it as the organofluorine burden in the environment. It's a way that it may provide an approach to getting a better mass balance between the PFAS that you measure versus the potential PFAS in the environment. There are different approaches to analyzing the total organic fluorine. One is PIGY, particle-induced gamma emission, and it's typically done. I mean, there's really only a couple of sources. Probably the most prolific in terms of publication is Grant Peasley out of Notre Dame. Combustion ion chromatography is an area that we are looking at because it provides certainly a far more economical approach to determining how much organic fluorine is in your sample. We've also been doing some work with neutron activation analysis, where fluorine, if you activate it in a nuclear reactor, you can measure the emission, the gamma emission coming off the atom. Again, not to get into too much chemistry, but if you can partition the organic fluorine from the inorganic fluorine, all of these three methods give, I think, will give an important piece of information in determining the total, as I say, organofluorine burden on your site. And then, the needs in the future from a remediation standpoint are the remedial technologies. And these are effective technologies for remediating and more so treating PFAS contaminated sites, treatment technologies for all PFAS, not just the target compounds. And, they have to be economically achievable. Where's the market going? Well, it's not going away anytime soon. This is a site contamination map in the United States, and there are 1,398 sites in 49 states. That was last year. These numbers are expected to grow, and the density of the sites to grow significantly. You can see the hot spots: Michigan, the Eastern Seaboard, New Jersey, North Carolina, and some sites in California. But because, as I said, because of the ubiquity of these compounds, expect the number of dots in other locations to increase. When it comes to the demand for remediation, you think about the work that we typically do: hydrocarbons, metals, volatile organic compounds. This is from a publication, Environmental Business Journal, from last year, that they did a very extensive market survey. PFAS, other emerging contaminants, and 1,4-dioxane are getting a lot of interest, and the expectation is that the demand for remedial efforts for these compounds is going to grow moving forward. I like the fact that 1,4-dioxane is another one of these compounds that people are calling it emerging. Well, it's been emerging a couple of times, but it is, again, a compound of emerging environmental concern versus the traditional hydrocarbons, heavy metals, PCBs, etc. You can see that the demand for PFAS is not going away anytime soon. They started looking at some of the remediation costs in the United States. So when I look at the United States and I think of Canada, I think, okay, let's look at a tenth. But the anticipated U.S. remediation costs, and this is from cradle to grave, from characterization to delineation to treatment. You're looking at $160 billion. That's a billion with a B. And it's really focused in 3 areas: Department of Defense, manufacturing sites, so places where they manufactured PFAS, and airports. Public perception and public, the impact of the public and the influence of the public on the regulators. Market considerations, well, many people have seen on Netflix, there's a program called The Devil We Know. It is a documentary on the Chemours facility in Fayetteville. And so if you haven't seen it, might be worth a look. But also last year came out Dark Waters, and with Mark Ruffalo, and this again speaks to certainly there's, I'm sure, a lot of literary license to make it exciting. It speaks to PFAS contamination in the environment. So these are all things that we consider in terms of where is the market going. There were resources presented before. I'll just show you again. The ITRC published last year a very extensive and detailed list of fact sheets. The information was culled from a very large working pool of industry stakeholders. These are folks that are working in the PFAS industry. Last year, the EPA published their action plan, where they're taking the world of PFAS. Given the societal dynamics in the U.S. right now, we don't know. The workload has not decreased for us, and in fact, it looks like it's going to continue to increase. And then, like I say, if you have an opportunity to look into the Environmental Business Journal that was focused on PFAS. As I said before, I like to acknowledge the people that do the work. I'm very privileged. I get to work with and engage some really, really smart people. So, in terms of the analytical methods, the operation, it's Adam Robinson and his group, Sinchi Chia, Colm McNamara, and Alicia Wilson. From a project management perspective, Stephanie Paulin, Melissa DeGracia is still with us, but she's focusing on managing our high-resolution mass spectrometry group now. But she put a lot of work into the development of our PFAS offerings. And then from a research and development standpoint, we have Dr. Heather Lord, Dr. Pat Benvenuto, and Lucy Kachatrian. So with that, again, I may have used up my time. Sorry about that. Maybe there'll be time after Lindsay's presentation. Sorry.
Thanks so much, Terry. We do have 2 minutes if
sure. Anybody have any questions?
I'm just looking at the pane here. I don't see any questions yet.
I did have a question, Terry. It's Lindsay.
Yep.
So BVL's been analyzing for GenX and Adona and F53 for a while. What's your sense of the presence of those chemicals in Canadian samples?
I'm not sure, to be honest with you. I know we see it in the U.S., but I don't have a good sense on the Canadian samples.
Great.
But I'll get back to you on that one.
Okay. Thank you so much, Terry. We'll switch to our final presenter for this session, Lindsay Patterson and Ian Mitchell. Let me just see here.
Great. How's that looking, Sarah?
It looks good. Looks great.
Okay, great.
Thank you, Lindsay.
Okay.
I'll let you
Yeah,
go.
no problem. I'm a senior scientist, senior soil scientist at SLR, and Ian Mitchell and I have worked together for many years, including about 14 years, investigating, remediating, and risk managing PFAS contaminated sites. I'll let Ian maybe join us, and maybe you can introduce yourself now.
Sure, thanks, Lindsay. So I'm a hydrogeologist. I've been with SLR for 25 years, and I manage the hydrogeology team for SLR's Canadian operations. And I'll pass it off to you to start off, Lindsay. Lindsay, thanks.
Great. Well, a big thank you to the Environmental Services Association Alberta, the sponsors, and Joe for organizing this online version of the EnviroTech conference. It's very appreciated. I'd like to express my gratitude for being able to deliver this material from the ancestral and unceded territory of the Syilx people in the Okanagan Valley. Persistent organic pollutants are of great concern to Indigenous communities due to the potential for impacts which can last many, many generations. This afternoon's presentation that Ian and I will be giving will share some of the key messages from the PFAS guidance document that was prepared on behalf of the Society of Contaminated Sites Approved Professionals of BC, or CSAP. It's easier to say, just call them CSAP. And the guidance was released online, so it's publicly available as of last June. So some of you are probably wondering about the title. I'm still not sure what BC's two best exports are, truly. Some of you may have your own ideas, but wine, I think, should be at least one of the two, in my opinion. I say this not only because I'm based in the beautiful Okanagan Valley, but also because 20 years ago, when I was starting out in the environmental industry, I had visions of a career in viticulture and fully immersing myself in the wine industry here. And sadly, that dream came to a crashing halt after about 8 months of studying, when I learned during my spring practicum that I was horrifically allergic to grape pollen, which unfortunately is a bit of a career limitation in viticulture. But back to the export, which is the focus of this afternoon's talk. In November 2017, the BC Ministry of Environment and Climate Change Strategy released soil and water standards for 3 specific PFAS chemicals. As PFAS were newly regulated substances under the BC Contaminated Sites Regulation, or what we call the CSR, CSAP retained us, SLR, to develop a guidance document for the investigation and remediation of PFAS at contaminated sites in British Columbia, to serve as a resource for CSAP members, regulators, and other contaminated sites practitioners. This presentation is really only a very high level summary of the information contained in the guidance, as it would be a challenge to cover all of the 70 pages of material in just a 25-minute talk. So as we've heard this afternoon, PFAS are man-made chemicals that have been used in the manufacturing of a wide variety of consumer and industrial products, and in firefighting foams, and in other specialized applications. At this point in the afternoon, you'll be aware that the term PFAS encompasses a very large group of chemicals. As Matt pointed out, many thousands of them. In BC, it is only a particular subset of PFAS called the perfluoroalkyl acids that are the focus of regulation under the CSR. The acids can be further subdivided based on the N group associated with the chemical, whether a carboxylic acid or a sulfonic acid. And the 3 individual PFAS regulated under the CSR are circled here. And they include perfluorobutane sulfonate, PFBS, which Terry talked about, PFOS, or perfluorooctane sulfonate, and perfluorooctanoic acid, or PFOA. As well, in the upper right-hand portion of the slide, I've included precursors to highlight that these chemicals have the potential to degrade to the regulated perfluoroalkyl acids over time. Now, even though only 3 individual PFAS are regulated under the Contaminated Sites Regulation, the guidance document does discuss other non-regulated PFAS that are expected to co-occur with the regulated compounds at contaminated sites. This information was included to assist practitioners in the management of sites for due diligence purposes. And in my opinion, it's very likely that many of these compounds will be regulated in the future. It may take a while for the regulations to be developed, but I fully expect that eventually they will be. Why was there the regulatory focus in BC on the perfluoroalkyl acids? Well, as Terry's pointed out, it's because of their persistence, their potential for bioaccumulation in food webs, the fact that they have known human and ecological health effects, and that they can actually be quite mobile in the environment, particularly in aqueous systems. Now, 14 PFAS had originally been identified as high priority substances by the ministry in 2016 and 2017 during the development of the updated CSR standards. However, standards were only eventually derived for 3 chemicals based on the availability of toxicological information from specific sources like the United States Environmental Protection Agency at that time. So soil standards were developed for 2 of the chemicals, drinking water standards were developed for all 3 chemicals, and an aquatic life protective groundwater standard was developed for PFOS only. But if you look closely at the footnotes associated with the regulations in BC, you'll see that all of these standards only apply to sites used for specific industrial or commercial activities outlined in Schedule 2 of the Contaminated Sites Regulation. So what are these industrial and commercial activities? Well, one is related to fire retardant manufacturing and wholesale bulk storage. Another is related to metal plating and finishing. A third is related to aircraft maintenance, cleaning, and salvage. And the final activity covers sites that have been or likely have been contaminated by substances migrating from other properties. I've been told by the Ministry of Environment that as the standards are written, if a property has been impacted by PFAS from another site, the type of activity occurring at the source site can include more than just aircraft maintenance, fire retardant storage, or metal plating for the regulations to apply to the affected property. To that end, it's critical that practitioners understand other significant sources of PFAS not specifically listed in the regulations, and some of these other sources are provided in the guidance document, and Ian's going to highlight a couple of them shortly. The CSAP guidance document provides detailed information on the point sources of relevance under the BC regulatory regime. The Schedule 2 use of fire retardant manufacturing and wholesale bulk storage is presumably intended to capture sites at which fluorine-containing foams, such as the ones discussed earlier by Matt, have been stored, handled, or used in large quantities. I would note that the regulations refer to wholesale bulk storage and not simply bulk storage. And this could be a bit of I guess a gap that the ministry is probably going to address down the road. Not all areas where firefighting chemicals were stored or used will be sources of PFAS. As we learned earlier from Matt this afternoon, these chemicals are associated with flammable liquid or Class B foams. Forest firefighting chemicals are generally comprised of Class A fire extinguishing materials and are not expected to be sources of PFAS. Areas where emergency response personnel would have trained with PFAS-containing foams are potential point sources, and frequently these have been situated at airports for obvious reasons. However, firefighting training areas are not the only locations where those foams may have been historically released. The guidance document really emphasizes the need for the conceptual site model to identify all areas where PFAS-containing materials are or have been stored, used, released, or disposed, including operational areas, unplanned release areas, and waste discharge areas. And some of those are highlighted here on the slide. Foams will have been used to prevent ignition of flammable liquids during fires and spills. To that end, firefighting foams could have been deployed at non-airport sites, such as large-scale petroleum facilities. However, as noted earlier, given that the Schedule 2 use refers to wholesale bulk storage of fire retardants, it's unclear whether storage and deployment of Class B foams at petroleum facilities are captured by the CSR standards. Regardless, the Environmental Management Act in BC prohibits the creation of pollution. So from a due diligence and more high-level regulatory perspective, this is probably a very minimal gap. The second Schedule 2 use linked to the PFAS standards is the result of the use of PFAS in fume suppressants for the metal plating industry, particularly the chrome plating industry. And Terry mentioned earlier about how some of these replacement compounds like F53 have been linked to that type of use. PFAS have been used for health and safety purposes in chrome plating to minimize worker exposure to hexavalent chromium vapors. Data from groundwater collected at one chrome plating facility in BC is shown here. It clearly demonstrates that use of such products can result in the release of PFAS to the subsurface at concentrations exceeding regulatory limits, and in this case, exceeding the CSR drinking water standard for PFOS. It's expected that the Schedule 2 use related to aircraft maintenance, cleaning, and salvage was primarily intended to capture airports and the probable use of firefighting foams at these types of facilities. Matt showed this slide or map a little earlier. It's from the research done at the Environmental Services Group of Royal Military College in 2018. And they published a study which looked at estimating the number of Canadian airports potentially contaminated with PFAS from Class B foams. And they estimated that approximately 175 airports in Western Canada were considered to be likely or potentially contaminated with PFAS. But beyond firefighting foams, there are aviation products that are known to include PFAS, which may be present at airports, and the guidance document summarizes the available but limited information on the presence of PFAS in these materials. And at this point, I will hand the presentation over to Ian.
Thanks, Lindsay. If you can advance to the next slide. Okay, so with respect to the contaminated sites regulation in BC, there's other sources of PFAS that practitioners should be aware of that aren't listed as a Schedule 2 industrial use. These include landfills, wastewater treatment plants and lagoons, and areas where biosolids have been applied. So it's important to understand the PFAS concentration characteristics that are associated with these types of sites, and these are addressed in the guidance document. For example, the landfills tend to have higher PFAS concentrations, but relatively low volumes of leachate, whereas wastewater treatment plants have low concentrations, but tend to have far higher volumes. Furthermore, the biodegradation processes in wastewater treatment plants are not effective at reducing the PFAS concentrations. Based on studies that have been conducted in Canada, there's generally 4 predominant PFAS that are measured in landfill leachate. These are the PFHXA, the PFPEA, PFOA, and PFOS. And at many of these landfill locations, the leachate gets directed to wastewater treatment plants. The example data here shows that the perfluoroalkyl acids such as PFOA and PFOS have been measured in Canadian landfill leachate at concentrations above the CSR drinking water standards. Researchers investigating PFAS at Canadian wastewater treatment plants have also reported that the PFOA was the most frequently detected PFAS, followed by PFOS and PFHXA. So median concentrations in wastewater effluent were generally found to be low. However, some research have found that the concentrations of PFAS have been up as high as 1.3 micrograms per liter at some treatment plants, and this is about 250 times higher than the median level. It's also important to understand that researchers have found that concentrations of dead-end PFAS, or perfluoroalkyl acids, are frequently higher in the effluent than they are in the influent. And if you recall, dead-end means that they essentially don't degrade beyond this point. That's the end point. And this is particularly true where the treatment includes an aerobic biological component. The reason for that is that the presence of precursors in the influent, which then undergo transformation to the perfluoroalkyl acids during wastewater treatment. Now, so PFAS also make their way into the biosolids that are generated from wastewater treatment. And in BC and Alberta alone, over 80,000 dry tons of biosolids are produced annually, with a significant proportion of that being applied to agricultural land as a beneficial reuse of the materials. Of course, that's subject to provincial regulations. This is also an approach that's been endorsed by the Canadian Council of Ministers of the Environment. And in one study from 2014, the median level of PFAS was found to be 13 nanograms per gram. And of particular interest, the study reported a maximum PFAS concentration from one treatment plant that was about 500 times higher than the median. And this highlights the potential for the PFAS inputs to originate from sources other than consumer products. So I'm going to shift gears now to laboratory considerations for investigation. There's two methods for analysis of perfluoroalkyls in soil and water that were approved by BC Environment in 2017. However, these methods outline performance-based requirements and they aren't prescriptive analytical procedures per se. So site investigators should be aware that all labs employ an in-house developed method. So from lab to lab, there will be differences in some aspects of their methods. Of particular note in the BC Lab Manual are the requirements for handling sediment in aqueous samples. Specifically, PFAS associated with sediments in water samples has to be extracted separately, and then the associated results reflected back in the final reported concentrations. But this isn't what was done historically by commercial labs. The BC Lab Manual also requires that labeled PFBS, PFOA, and PFOS quantification standards be used at a minimum, as opposed to using one quantification standard for all three. So in particular, practitioners should confirm that their project lab is using a labeled standard for PFBS. As well, the lab manual specifies hold times that may be shorter than those specified in the lab's own in-house method. So the take-home message is that the requirements for analysis of PFAS on lands under provincial jurisdiction may not be met by the in-house method offered by your contracted lab. So it's important that project managers liaise with their labs prior to collecting samples and analyzing them in order to confirm that the method that's going to be employed will meet the provincial requirements. The guidance document also highlights a number of key considerations for the site assessment of PFAS. These include site-specific factors such as understanding the interactions between impacted surface soil and surface water, such as precipitation, irrigation water, or surface runoff, given the frequent release of PFAS-containing materials to surface soils at some sites, such as the AFFF application or perhaps spillage. It's also important to understand the groundwater surface water interactions, such as seasonally inundated conditions and the potential for discharge to surface drainages, particularly in British Columbia coastal areas. And finally, it's important to understand factors that may affect groundwater transport processes, including the presence and depths of pumping rates of groundwater extraction wells that might be in the vicinity of your source area. Given the potential for extensive groundwater and surface water transport of the perfluoroalkyl acids, site investigators should give consideration to potential receptors at significant distances from the source areas. PFAS have been found to travel several kilometers in groundwater, and in fact, they've even been found to go hundreds of kilometers in surface water. So for those reasons, it's recommended that PFAS investigations be expedited where there's any potential for impacts to off-site receptors and in particular to drinking water consumers. This is what's typically known as the outside-in approach. Due to the partitioning behavior of the regulated PFAS in BC, both soil and groundwater are considered media of interest. Additional media to consider with respect to the application of risk-based standards, as well as for due diligence, would be surface water, drinking water, dust, sediment, and biota tissues. So if you've attended other presentations about PFAS, you'll know that there's a lot of field precautions that need to be considered when you're conducting your PFAS site assessments. These include not using personal hygiene products before going into the field, avoiding fast food products, so no stopping for coffee and egg McMuffin on the way to the site, and avoiding the many types of clothing material that could potentially give rise to false positives, such as Gore-Tex and Visivests. So given all these extensive limitations on products and clothing that we normally use, how does one defensively sample for PFAS in the field? Seriously though, to provide an appreciation of how sensitive the QA/QC issues are with PFAS compounds, consider that we're used to working with contaminants that are regulated in the parts per million or parts per billion, while some of the PFAS compounds are regulated in the parts per trillion. So by analogy, if you were to drink water that was laced with PFOA equal to its standard in BC, and if you drank 8-ounce glasses of that water 365 days a year for a lifetime of 80 years, over that time, you'll only have consumed about 3 or 4 drops of PFOA. So it gives you an appreciation of just how minuscule these concentrations are that we're speaking about. So as a site investigator, the challenges associated with characterizing the PFAS contaminated sites start at the project planning and initiation stage. And due to the prevalence of PFAS or PFAS-related compounds in a variety of consumer materials, as well as the surface activity of the compounds, investigations require specialized precautions above what's considered the norm, and you have to account for those during the design and planning stages of your investigation. Many of the materials that we normally use are not acceptable when investigating for PFAS due to the potential for introducing low levels of the contaminants. So the guidance document provides a compilation of materials that should be avoided in field programs, in addition to a list of materials that are considered acceptable. It also reviews considerations for pre-testing water sources used in assessment programs, whether it's for the collection of your QA/QC blanks or for decontaminating equipment, which can be incredibly onerous, especially when working in source areas. And the guidance document also lists specific considerations for a number of other items, including drilling, well development, sampling of soil, groundwater, surface water, sediment, and drinking water. So the importance of analyzing blanks during PFAS site assessments can't be overestimated. From the measures necessary to prevent cross-contamination in the field during drilling, soil sampling, groundwater monitoring, and water sampling, to those measures necessary to tease out potential cross-contamination at the lab, you need to analyze blanks, and a lot of them. The guidance document reviews a number of other QA/QC considerations, including lab detection limits and laboratory QA/QC matrices. From experience, it's critical to consider the lab data in the context of what you know about the conceptual site model. So if the lab data isn't making sense within your CSM, then there's a good chance that it may be related to cross-contamination, or maybe even the introduction of PFAS to your samples from other sources. With respect to the remediation of PFAS compounds, the guidance document reviews field-proven options for both soil and water. And this slide focuses on the unique properties of PFAS that make them highly resistant to environmental degradation. And this is why they pose such a challenge for remediation. So one widely implemented approach to reduce PFAS concentrations in surface water or groundwater is to excavate the source materials and place them in engineered cells. If you're to do that in BC, that would require a waste discharge authorization from the ministry. Another option for soil remediation is incineration, But of course, the associated costs can be prohibitive if you're dealing with large-scale source removal. Some companies also advertise the incorporation of proprietary soil additives to absorb and stabilize PFAS, but the long-term efficacy of those solutions is still under evaluation. So while you might be able to stop a plume from further migration, the mass still remains in the ground. Other trials are being conducted using soil washing, in situ chemical oxidation, but these also have their challenges. In particular, the in situ chemical oxidation is known to be effective, is not known to be effective on the perfluoroalkyl sulfonates, and can actually result in the generation of more mobile PFAS from precursors. Thermal desorption technologies is another area of focus for the treatment of PFAS contaminated soil. So because the dissolved phase groundwater plumes can be pretty large, it's often more practical to target source removal followed by endpoint treatment rather than attempting to remediate the entire plume to very low target levels. So the majority of groundwater remediation research has been focused on pump and treat methods and optimizing the removal of PFAS using sorbent media, such as granular activated carbon or ion exchange resins, or also by filtration methods such as reverse osmosis or nanofiltration. In Australia, foam fractionation is being used by the Department of Defence at one of their sites. With foam fractionation, air is used to promote the migration of PFAS to a foam phase, and the foam then gets extracted and further reduced. Some sort of sorbent technology is usually still required to reduce the PFAS concentrations to levels that are suitable for discharge, but it may be useful for extending the life of the sorbents. The generation of a high concentration foam waste could be significant though with that process, depending on the volume of water that requires treatment. PFAS currently aren't regulated under the BC hazardous waste regulation. So the contaminated sites regulation standards apply to the disposal of PFAS contaminated soil at landfills in British Columbia, except where landfills have a permit that specifically outlines the maximum allowable limits for the disposal of the PFAS contaminated wastes. And in addition, keep in mind that some individual facilities may implement operational thresholds for PFAS contaminated materials at concentrations that are below the BC CSR standards. It's also worth noting that based on United Nations guidance under the Basel Convention, materials with a total PFOS concentration of 50 milligrams per kilogram are not considered suitable for landfill disposal. So the Environmental Management Act, it prohibits the introduction of waste into the environment in such a manner or quantity as to cause pollution. So practitioners should review their PFAS data for wastes that are intended for landfill disposal in consideration of the Basel Convention requirements and the potential for the material to cause pollution. And you should also contact your disposal facilities directly to discuss the operational thresholds they have for PFAS at that specific facility. And for materials that exceed the Basel Convention threshold of 50 milligrams per kilogram, it's likely that waste will need to be incinerated or otherwise disposed of such that the PFOS content is destroyed or irreversibly transformed. Okay, so that's a bit of a whirlwind tour, and we recognize it's a lot of information to digest. It's also important to note that there's a lot of research currently being done in PFAS, so the state of knowledge is evolving rapidly. That said, there's a wealth of information in this guidance document, and we think that practitioners, regulators, and other stakeholders will find it extremely useful, regardless of which province you reside in. So I thank you for your time, and if there's any questions, Lindsay and I will do our best to answer them.
Thank you so much, Lindsay and Ian. We have 2 minutes for questions, and we do have a question in the question pane here from Wendy Conserata. She's asking if there are any Alberta-specific regulations on PFAS.
So what I've been told is that Alberta Environment will be developing Tier 1 guidelines once the CCME has finalized their soil and groundwater quality guidelines for PFOS. And my understanding from talking to people who are involved with that committee at CCME is that they're really in the final stages of issuing those guidelines. So COVID might throw a bit of a wrench on how quickly they get out, but I think we should be seeing them within the next, let's say 3 to 4 months. I'm going to be optimistic. Yeah.
Lindsay, is that just for PFOS only?
Yeah, the CCME guidelines are just for PFOS.
Yeah.
There is my understanding is the committee is also working on guidelines for PFOA, but I haven't been able to get any updates on the progress on that.
Great. Thank you so much. That looks like all the questions, and it is 2:59, so I'm going to turn it back to Joe here.
Can I ask one more question, just of Lindsay? The CSAP guidance document, is that available for public consumption, or do you have to be a CSAP?
No, it's available on the web. Just if you Google CSAP PFAS guidance, it should take you to the CSAP webpage, and yeah, you can download it from there.
Yeah,
Beautiful.
you just Google CSAP Society, and then they have a menu and look under the professional development library, and you'll find it there.
Beautiful, thanks. Great presentation.
Thanks.
Yeah, I'd have to agree. That was a great way to end the conference. There's a lot of information there, and I think we could do a longer day just on this topic. So I'd like to close by thanking all the sponsors. Without this, wouldn't be possible, so we really appreciate that. Thank you to the presenters. It isn't easy presenting over this format. You don't have the reaction of the audience to help you along, and but I think it still worked good. I've been receiving lots of feedback from people through email, so I really appreciate that. Keep the feedback coming by email to me with suggestions of what we could do different, what you enjoyed, what other things we could do. Thanks to the moderators. Thank you, Zara, today for this session. You did a great job. Thank you to all the attendees who signed up and supported ESA during this time. 90% of ESA's revenues are from events, so it's a tough struggle right now. We're making it through, and your support really, really helps. Secondly, the presentation videos will be available in a couple days. I think a couple more are just being processed and get uploaded. Once that is done, I will send out an email with a link to that. They'll be available for you as registered attendees for about 6 months because you've paid for that. Now I think we'll open it up to everyone. Another announcement is ESA has a survey out right now about the site rehabilitation program that the Alberta government has. We'd like your feedback so that we can supply them with some information so that they can tweak or improve, tell them what's working, not working with the program so we can make it better. And finally, I'm just going to leave you with this slide. Never look back unless you're planning to go that way. I think that's kind of timely for the period that we're in right now. So I'm going to leave you with that. Have a great summer. Thank you for your support and stay safe.
Thanks, Joe.